Hello again. Today we're going to talk about ozonolysis and hydrogenation. So let's start with ozonolysis. This is a really cool reaction that allows us to basically cut a double bond in half. Or another way to say that is we're going to cleave double bonds. Okay, so let's start with an example just to kind of show you what's going on here. Let's start with cyclohexene. And I'm going to draw the hydrogens that are attached to this double bond because that's going to be important in our products. But in ozonolysis, we're first going to add ozone, which is O3. And then in the second step, we're going to add a reducing agent. So there's a couple of options here. We can use something called DMS, which stands for dimethyl sulfide. Or we can use zinc and water. So those are reducing agents. So I'll just highlight those. Okay. Now remember, oxidation versus reduction. So in oxidation, we're typically adding an oxygen, for instance, but with reduction, we're removing an oxygen. Now you could also talk about oxidation and reduction in terms of electrons, but here we're specifically referring to oxygen. And then I'll also add here that DMS stands for dimethyl sulfide. So DMS. Okay, so what happens when we add ozone and a reducing agent to a double bond? Well, we are going to basically cut that double bond in half and add an oxygen to each of those halves. So let's show what that looks like. All right, so we cut our double bond in half and we added an oxygen to each of those halves. So now we actually have two aldehyde groups. And we can redraw this as well. So since there's only single bonds now, and we're not in a cyclic ring anymore, those single bonds can all rotate, and we could redraw this to show those two aldehyde groups on either end of the molecule. So if you're a little rusty on your functional groups, definitely go back to your notes from 161 and just kind of review the names of different functional groups. But remember that an aldehyde has a carbonyl group, so a carbon double bonded to an oxygen, and then we also have a hydrogen bonded to that carbon. Now, depending on what type of double bond you have and what's bonded to the double bond, you can turn an alkene into aldehydes or into ketones. So instead of a hydrogen bonded to that carbon, you would have another carbon group bonded to that carbonyl carbon. And that would be a ketone. Okay, so kind of going back to the reducing agents, I'm actually going to draw what dimethyl sulfide looks like here, just so you can get an idea of that. So there's a sulfur in the middle and two methyl groups are on either side. And at the end of this reaction, the third oxygen in ozone, you'll notice, is not in our product. So that third oxygen actually ends up with the reducing agent. So, for instance, if you use DMS, that's going to become DMSO, or dimethyl sulfoxide. If you use zinc, that's going to become zinc oxide. And you can use either reducing agent. Dimethyl sulfide is quite smelly because of that sulfur atom that's present. Sulfur tends to be smelly no matter what it's in. But that might be easier to use than zinc, which is a solid metal. So it might be hard to use depending on what's available. All right. So let's get some practice in with ozonolysis. Let's look at a couple of examples. All right, so let's start with an alkene that has two ethyl groups that are cis to each other, and then two methyl groups that are cis to each other. And we're going to use ozone, and let's just use zinc as our reducing agent. Okay, so what I would like you to do is try to predict what the products are. So if you want to pause the video, you can, and when you unpause, we'll go over it together. Okay, so let's see what our products would be here. So again, we're cutting our double bond in half, and we're going to add an oxygen to both of those double bond halves. All right, so we would end up with two molecules that look like that. If we rotate them, or even if we just look at them here, we can see that they're identical. And actually, I'm going to redraw these. So I'm just kind of turning them on their side and flipping a couple bonds there. But these are the same molecule. And this is actually 2-butanone. Now, are these aldehydes or ketones? Ketones, because the carbon that's double bonded to an oxygen has two other carbon groups attached. So that would be a ketone. And we'll learn how to name ketones later on, so don't worry about that right now. Okay, let's try one more. What if we have an alkene with two hydrogens on one side and then a carbon group on the other side? So a methyl and a propyl group. And then let's add ozone and zinc with water. So if you want to pause the video and try this on your own, you can, and then we will go over it together. Okay, let's see what we've got here. So if we cut this double bond in half and add oxygens, let's see, one of our carbonyl groups is just bonded to 2 hydrogens. Okay, and the other one will be bonded to a methyl and a propyl group. All right, so these are different, and you'll notice that in our first example, we had a symmetrical alkene. So we ended up with the exact same product after we split the double bond in half. But here we have an asymmetrical alkene, so we end up with 2 different products. So we have a mixture. So that can play an important role if you're trying to just end up with one product. You might have to pick a starting material that is symmetrical. All right, so the first product we formed here is actually called formaldehyde. So this is what's used to preserve bodies, and it's quite smelly. And we've also more recently determined that it is carcinogenic, which means it can cause cancer. So scientists have tried to find other ways of preservation. And then our other product is a ketone, and this is called 2-pentanone. And again, we'll learn how to name all these things later. All right, let's try a slightly harder one. So let's do a challenging problem, or a more challenging problem, I should say. All right, so let's look at a bicyclic compound. I know these are everyone's favorites. And let's see, we just have hydrogens across the double bond there. All right, so if we perform ozonolysis on this bicyclic structure, what would our product or products look like? So if you want to pause the video and try this on your own, you can. And then when you unpause, we'll go over it together. Okay, so let's cut our double bond in half. And I'm also going to number the ring that's on the left-hand side just to keep track of my carbon atoms. Because remember, there are 2 rings here. So even though we're cutting open one of the rings, the other ring is still intact. So we still have this ring that I'm highlighting in yellow. So that is still intact. So let's number those carbons. So 1, 2, 3, 4, 5. Okay, so that tells me that I still have a 5-membered ring. And then it looks like beyond that, I have this bond here. And then on the other side, I have another bond. So I've got a carbon with a double bond. So I've got a carbon with a double bond. And we know that those double bonds will end up with oxygens on them. And then we have a hydrogen attached as well. So we've got our 5-membered ring that I'm highlighting in yellow. And then we've got our blue group off to the right, and we've got our purple group off to the left. And you can also see that when you number the ring. So if you don't have highlighters available, you can also number the ring and see where those groups would exist. So this one's a little more challenging, but you can create some really cool compounds using a bicyclic alkene. So are those groups that are attached to the ring aldehydes or ketones? They're aldehydes because they have a hydrogen attached. So we converted an alkene into two aldehyde groups. Okay, so let's move on to catalytic hydrogenation. All right, so this is a very useful process that will convert an alkene to an alkane. So we're going to take a double bond and turn it into a single bond. So we're just going to add hydrogens across a double bond. So let's start with cyclohexene again. And we're going to add hydrogen, so H2, and then we're going to add a catalyst. So it's really hard to break apart a hydrogen bond because hydrogen molecules are quite stable. So you need some sort of catalyst in order to get the hydrogen atoms to split apart. There are a couple of catalysts you can use, such as platinum, PT, or you can use palladium and carbon. All right. So remember that when you add a catalyst to a system, it's going to change the pathway that the reaction takes. So you're going to have a different activation energy, and it's going to be a smaller activation energy. Oh, I actually should also add that you could use nickel here too. That's another metal that will work. All right, so this is actually an example of surface chemistry because what ends up happening is the hydrogen molecule will attach to a surface of these metal atoms. So let's say these are hydrogen atoms, and eventually they're going to split apart. So you'll get the hydrogen atoms kind of moving around the surface of the metal. Actually, recently during the pandemic, people have been stealing catalytic converters from cars, specifically cars like Priuses, so electric cars. And part of the reason for that is you can sell them, and they do have catalysts like platinum in them. So you can get some money for those. Maybe I shouldn't have told you all that. You're going to become criminals stealing catalytic converters. But if you've wondered why people are stealing catalytic converters, that's why. Okay, so this is actually going to end up producing a alkane, so we'll get cyclohexane as a result. And hydrogen is actually going to add syn. So we'll have syn addition here. So you can imagine if other groups are bonded to that double bond, they would end up syn to each other as well. So what if we had, two methyl groups there on the double bond? They would just be back here. So they'd be syn to each other as well. Now, the reason that syn addition occurs and not anti-addition is because of the surface chemistry that's going on. So you can imagine as an alkene kind of comes in to that surface with the hydrogens on it, the hydrogens can really only add to one side. They can't add to opposite sides because they're stuck in place on that surface. And your textbook actually has a much better picture of what's going on here. So I encourage you to look that up. It's a little bit easier to visualize. All right, so let's actually look at another example. Let's look at vegetable oil, which has cis fatty acids. So vegetable oil has double bonds in it, and those double bonds are in the cis form. So this is vegetable oil. And again, that R group is just some alkyl group. Now, vegetable oil, as we know, is a liquid. And then let me just write cis fatty acid here. Now, what if we add hydrogen to this vegetable oil? What would we end up with? Well, we would add hydrogen across that double bond and turn it into a single bond. All right, so this is actually hydrogenated vegetable oil. There's actually a really famous brand of hydrogenated vegetable oil that's called Crisco. So you might use that in your baking or cooking. But this is a solid. So we went from a liquid to a solid when we hydrogenated the vegetable oil. Okay, so just kind of a real world example. All right, so we've talked about these catalysts, platinum, palladium, nickel, and let's look at an example here. So let's say that we have an ethyl group on both sides of that double bond. And then we add hydrogen. And then let's say we use palladium mixed with carbon. What would our product be? And feel free to pause the video and try this on your own, and then we'll work on it together. Okay, so we said that hydrogen will go through syn addition. So let's say they add from above. The ethyl groups will be behind the plane, and they'll be syn to each other. Okay, what if we added the hydrogens from below? So what if they were in the dashed position and the ethyl groups were in the wedged position? what's the relationship between these two products? Are they enantiomers, diastereomers, or identical? So they are identical. There is a plane of symmetry here, so this is a meso compound. And you can also rotate and flip one of the products to see that it matches the other one. So I'll just erase the other product since they're the same. Now, another thing just to keep in mind is when we're using a metal catalyst, this is actually called a heterogeneous catalyst. And that's because it doesn't mix with the reagents or the reactants. So the catalyst does not dissolve in whatever our solvent medium is, which is typically a liquid. So we'll just write that the catalyst does not dissolve. And this can, be difficult to deal with. Can be difficult to perform your reaction if you can't dissolve the catalyst. So there is another catalyst that we can use, and it's shown in the upper right-hand corner here. It's gigantic, very complex, with lots of phenyl groups attached. And you'll notice that there is a rhodium atom, RH, in the middle, surrounded by phosphorus atoms. And then those are all attached to multiple phenyl groups. There's also a chlorine in there too. So this is called Wilkinson's catalyst. Oops, I already spelled Wilkinson wrong. Wilkinson. There we go. All right. So, let's see. Okay, so let's draw an example showing the use of Wilkinson's catalyst. So let's say we have the following alkene. It has a methyl group up above, and then it has a double bond with a methyl group attached down below. So let's add hydrogen across the double bond, and then I'm going to abbreviate Wilkinson's catalyst as RH for the rhodium atom, Cl for the chlorine, and then we're going to abbreviate the phosphorus with the phenyl groups attached as PPH3, and then there are 3 of those attached to the rhodium. All right. So what we end up with here are 2 products. All right, so the methyl group up above, which is in a wedge position, will just stay in its wedge position. So I'll just write CH3 there. And then remember, we get 2 hydrogens that end up syn to each other. And then we have that other methyl group, which will now be behind the plane. Okay, so we actually have 2 stereocenters in this product, right? We have the one at the top, and then the one kind of to the bottom right-hand side. Now, those hydrogens, initially I showed them adding from above, but what if they added from below? So that methyl group on the top would stay the same. We're not touching that. But what if the hydrogens came in from below the plane of the ring? Oh, sorry, I keep hitting the next button. Well, that other methyl group that was attached to the double bond will now be in a wedge position. Okay, so we still have two stereocenters. One stayed the same, it didn't change, but the other one did change. So what's the relationship between these two products? Are they enantiomers, diastereomers, or identical? Well, if only one stereocenter changed, then these are diastereomers. Now, just because we used Wilkinson's catalyst, that doesn't mean we end up with diastereomers. Wilkinson's catalyst is just an easier catalyst to use sometimes because it does dissolve in a solvent. So this is actually a homogeneous catalyst. So it does dissolve. So I was just showing you another example of hydrogenation, but we were just using a different catalyst, just for fun, to see what would happen. And the same thing would happen as if we used platinum or palladium. Now, what's really cool too is a scientist by the name of William Knowles in the 60s, he developed a way to perform asymmetric hydrogenation, so anti-addition of those hydrogens. So he was using a chiral version of Wilkinson's catalyst, essentially. And with the chiral version, you can get a mixture of products, and you can kind of control a little bit, the stereochemistry of your products. So there would still need to be some method of separation. You don't get a completely pure product, but that is one way to kind of control the chirality of your product. So that's another use for Wilkinson's catalyst. All right, so you have learned a lot of different reactions and their mechanisms in Chapter 8. I know it can feel really overwhelming, so in the next lecture, we're just going to summarize addition reactions. So we'll go over all of the different reactions. We'll talk about whether they form the Markovnikov or anti-Markovnikov products. We'll also go over whether we have syn or anti-addition. And then we'll go over one of the study guides, which basically just has a big reaction map. And that can really help to study and remember all of these different reactions. All right, so I will see you in the next video.